Tonight, we're going to travel to the edge of everything we have ever known, to a place so far from home that the sun itself has shrunk to nothing more than the brightest star in a sea of countless others. Somewhere out there, right now, at this very moment as you close your eyes and let the darkness settle around you, a small golden machine is drifting through interstellar space. It has been travelling for nearly half a century. It carries the voices of whales, the sound of rain, a mother's first words to her child, and the music of a civilization that sent it outward with trembling hands and an open heart. And until recently, it was still talking to us. A faint whisper crossing 15 billion miles of absolute void, arriving at our antennas as a signal so weak it carries less power than a single snowflake landing on the ground. We were still listening, and then something changed. Here is the thing most people don't realize about Voyager. It was never supposed to last this long. It was designed for a 5-year mission, a brief tour of the outer planets, a handful of photographs, a collection of measurements, and then silence. But Voyager refused to go quiet. It kept moving. It kept transmitting. It crossed the boundary of our solar system, entered the true darkness between the stars, and still it sent its signal home. Engineers who were young when it launched grew old maintaining the connection. Some of them have spent their entire professional lives listening to a single spacecraft drift further and further away. There is something terrifying about that. Something almost impossibly beautiful. A machine built by human hands, now floating through a region of space no human will ever visit, still whispering, still alive, for now. But buried beneath the wonder of that story is a truth that rarely gets mentioned when people talk about Voyager. The silence is coming. Not as a dramatic explosion, not as a catastrophic failure, not as anything that will make the evening news with the urgency it deserves. It will come quietly. It will come the way all great things end, slowly and then all at once. The power source that has kept Voyager alive for nearly 50 years is fading. Its nuclear heart is cooling degree by degree, milliwatt by milliwatt. Scientists at NASA already know, with mathematical precision, when the last instrument will go dark. They know when the final signal will begin its long journey home. They know how long it will take to arrive, and they know that after it does, there will be nothing. Complete silence. Forever. By the end of tonight, you're going to understand exactly why that last signal matters so deeply. Not just as a moment in the history of space exploration, but as a mirror held up to something ancient and searching inside the human soul. You're going to understand what Voyager has been measuring in the cold dark between the stars, what it still carries on its golden record, and what it will mean for the men and women who have spent their lives listening when the frequency finally goes still. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a sound that almost no one has ever heard. It arrives at a handful of massive antenna dishes scattered across 3 continents. One in the California desert, one in Spain, one in Australia. And it comes from so far away that by the time it reaches us, it carries almost no energy at all. Scientists measure it in fractions of a watt. Less than the static you hear when you press your ear against a seashell. Less than the hum of a single grain of dust falling through a sunbeam. And yet, for decades, engineers have been sitting in the quiet glow of their monitors, listening to it with the kind of patient devotion that borders on the sacred. That signal is the voice of Voyager 1, and right now, tonight, as you settle in and let your breathing slow, that machine is still out there, drifting farther from home with every passing second. Let me give you a sense of the distance, because numbers alone never quite do it justice. If you could drive a car at highway speed, say 100 kilometers per hour, without stopping, without sleeping, without ever slowing down, it would take you roughly 500 years to reach the moon. The moon, which hangs so close to us that on a clear night you can see its craters with a pair of binoculars. Now imagine driving that same car to where Voyager 1 is tonight. You would need more than 17 million years. You would begin your journey while our ancestors were still learning to use stone tools. You would arrive in a future so remote that the continents will have rearranged themselves beneath the sea. That is not a poetic exaggeration. That is the arithmetic of interstellar distance, and it is one of the most quietly terrifying things I can offer you tonight. Voyager 1 is, at this moment, approximately 23 billion kilometers from the Sun. The signal it sends home travels at the speed of light, the fastest anything in this universe is allowed to move, and it still takes more than 22 hours to reach us. Think about that for a moment. Even light, even the very fastest messenger the cosmos permits, needs almost an entire day to cross the distance between us and this small golden machine. When mission controllers at NASA send a command to Voyager, they transmit it knowing that their message will not arrive for nearly a full day. And then they must wait another full day for any response. Every conversation with Voyager is a dialogue stretched across 2 days of silence. Every instruction, every question, every gentle course correction, sent and received across an abyss that makes the word vast feel embarrassingly small. And yet here is what I find most remarkable about all of this. We built Voyager in the 1970s. The engineers who designed its computer systems worked with technology less powerful than the device you use to set a kitchen timer. The spacecraft carries roughly 70 kilobytes of memory. Your phone carries billions of times more. The antenna that transmits Voyager's signal home produces about 22 watts of power, roughly the same as a dim light bulb, and from 23 billion kilometers away, through the frozen vacuum of interstellar space, that signal still finds us. Barely, faintly, but it finds us. There is something in that fact that feels almost like stubbornness, like the quiet refusal of something small and human-made to simply disappear into the dark without saying goodbye. There are people alive today who have spent more of their professional lives listening to Voyager than they have spent doing anything else. Engineers in their 60s and 70s who were young researchers when the spacecraft launched in 1977, who have watched it cross the orbits of Jupiter and Saturn and Uranus and Neptune, who were there when it entered interstellar space, and who are still there now, still showing up, still monitoring the signal, still making tiny adjustments to keep the connection alive. Ask them what it feels like, and many of them will pause before answering. There is a tenderness in how they talk about Voyager that you do not often hear scientists use when describing machinery, something that sounds almost like love, and I think that is because Voyager is not just a spacecraft. It is a record of what human beings chose to do with their curiosity when no one told them they could not. But tonight, I want to tell you about the silence that is coming, because as extraordinary as Voyager's journey has been, as improbable as it is that this small machine is still alive and still talking after nearly 50 years, the physics of the situation are not negotiable. Voyager runs on a nuclear power source, a radioisotope thermoelectric generator, which converts the heat released by the slow decay of radioactive plutonium into electricity. It is a beautiful piece of engineering, elegant in its simplicity. But plutonium decays, the heat decreases, the electricity produced grows smaller with each passing year, and there is a threshold below which Voyager's instruments cannot function, below which its transmitter cannot broadcast, below which the signal, however faint, will stop entirely. Scientists know when that threshold will be crossed. They have run the calculations many times. The number they arrive at is not centuries from now, or even decades. It is much closer than that. And when that moment comes, the silence will be absolute. I want you to hold that image in your mind as we begin tonight's journey together. Not as something frightening, but as something worth understanding. Because the story of Voyager's last signal is not really a story about technology failing. It is a story about what we chose to send out into the universe and why we chose to send it. It is a story about the people who dedicated their lives to maintaining a connection across distances that should have made connection impossible. And it is a story about what happens to the human heart when it confronts the reality that even our most courageous reaching has limits. Even our most defiant little machines must eventually go quiet. Even the longest goodbye must, one day, end. So tonight, let the darkness around you be a companion rather than an absence. Let the quiet of this hour be the right kind of quiet for a story like this one. Somewhere out there, moving at roughly 17 kilometers every second, a golden machine the size of a small car is crossing through a region of space no human being has ever visited and none ever will. It carries photographs and music and the sound of human laughter. It carries a diagram of where it came from, in case anyone ever finds it and wonders. And it is still, tonight, sending home its faint and faithful signal across the impossible dark. We are still listening. And for a little while longer, there is still something to hear. The year was 1977. The world was a very different place. The first personal computers were just beginning to appear in hobbyist magazines. Saturday Night Fever was playing in cinemas. The Cold War was still a daily reality, and the idea that a small nation could fit a supercomputer in its pocket would have sounded like science fiction of the most implausible kind. And yet in that same year, a small group of engineers and scientists at the Jet Propulsion Laboratory in Pasadena, California, were quietly preparing to do something that no civilization in the history of this planet had ever attempted. They were going to throw a bottle into the cosmic ocean. They were going to build a machine, load it with everything they thought best represented the human race, and hurl it outward into a darkness so vast and so permanent that no one in the room expected it to ever be found. Voyager 1 launched on the 5th of September 1977 from Cape Canaveral in Florida. Its twin, Voyager 2, had actually launched 16 days earlier, on the 20th of August, but the trajectories were designed so that Voyager 1 would overtake its sibling and reach Jupiter first. The launch itself was not a quiet affair. A Titan III E-Centaur rocket carried the spacecraft into the sky on a column of fire and noise that could be felt in the chest from kilometers away. And then, as the rocket performed its final burn and released its payload into the cold dark of space, something remarkable happened. The noise stopped, the fire stopped, and a small golden machine, weighing just under 900 kilograms, less than a compact car, began its journey toward the stars in perfect, absolute silence. The mission was originally planned around a rare alignment of the outer planets, an alignment that occurs only once every 175 years. Jupiter, Saturn, Uranus, and Neptune were arranging themselves in a configuration that would allow a spacecraft using the gravitational pull of each planet as a slingshot to visit all four in a single mission. Without that alignment, such a journey would require decades of additional travel time and fuel that no rocket of that era could carry. The window was narrow, the mathematics were demanding, and the engineers who designed the Grand Tour trajectory, as it came to be called, were working with slide rules and early computers in an era when a calculation that now takes a fraction of a second might occupy an entire afternoon. They got it right. They got it almost impossibly right. And because they did, two small spacecraft were sent on one of the most ambitious journeys in the history of human exploration. But I want to tell you about something that happened alongside the engineering, something quieter and in many ways more profound. In the months before Voyager launched, a committee was assembled to answer a question that no one had ever needed to answer before. If an alien civilization were to find this spacecraft, a civilization that had no knowledge of Earth, no shared language, no common frame of reference, what should we say to them? What would you say if you had one chance to represent everything humanity has ever been, compressed into a single object no larger than a dinner plate? The committee was led by the astronomer Carl Sagan, and the answer they arrived at was a gold-plated copper disc that came to be known as the Golden Record. The Golden Record contains 115 images encoded as analog signals, diagrams of human anatomy, photographs of landscapes, pictures of people eating and laughing and working. It contains greetings in 55 languages, including a message in an ancient Sumerian dialect that no living person speaks anymore. It contains the sounds of earth, rain falling on leaves, surf breaking against a shore, wind moving through trees, the crack of thunder, the song of birds, the low moan of a humpback whale singing in deep water. It contains music, Bach and Beethoven and Chuck Berry and a pygmy girl's initiation song and Azerbaijani bagpipes. It contains a spoken message from the Secretary General of the United Nations and a handwritten note from then-President Jimmy Carter that reads, in part, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. There is something about reading those words that makes the chest feel tight. Because Carter was right. We were trying to survive. We still are. The record is encased in an aluminum jacket, and it is designed to last. Scientists estimate that in the cold vacuum of interstellar space, shielded from the erosive forces that wear things down on Earth, the Golden Record could survive for more than 1 billion years. 1 billion years! The Earth itself is only 4.5 billion years old. The record carries instructions for how to play it back, encoded in the language of mathematics, the one universal tongue that any sufficiently advanced civilization should be able to read. Whether anyone will ever find it is, of course, deeply uncertain. The odds are, in the most honest assessment, extraordinarily small, but the people who made it understood that. They made it anyway, and I think that says something essential about the human animal, that we are a species capable of sending a love letter into the void with full knowledge that it will almost certainly never be read. What the engineers knew, even in those early days, was that Voyager was already doing something beyond its official mission. Yes, it would photograph Jupiter and Saturn. Yes, it would measure magnetic fields and particle densities and plasma temperatures across the outer solar system. All of that was the science, the justification, the reason the funding had been approved. But the act of launching something out of the solar system entirely, something built by human hands that would outlast every human institution, every government, every language, every memory of the people who built it, that was something else. That was not science. That was a statement. A defiant, tender, slightly irrational statement made by a species that had only just learned to fly, looking up at the stars and deciding that looking was not enough. There were 961 days between Voyager 1's launch and its closest approach to Saturn in November of 1980. 961 days of cruise, of silence, of slowly increasing distance, while the small team at JPL monitored its systems and waited. And during those days, something happened that none of the engineers had quite planned for. They began to feel attached to it. Not sentimentally, not irrationally, or perhaps a little of both. But the spacecraft had a personality, in the way that all complex systems cared for by devoted people eventually acquire one. It had quirks and preferences and a way of responding to commands that made it feel, against all engineering logic, like something more than machinery. It was theirs. They had made it, and launched it, and were keeping it alive across the growing dark. And in that relationship, between the makers and the made, between the stationary and the endlessly moving, something quietly extraordinary was being born. There is a moment in every long journey when the destination stops being abstract and becomes real. For Voyager 1, that moment came in January of 1979, when its cameras began resolving Jupiter from a distant smear of light into something unmistakably, overwhelmingly present. The largest planet in our solar system, a world so massive that all the other planets combined could fit inside it with room to spare, was growing in Voyager's field of view day by day, hour by hour, with a slow and terrible grandeur. Nothing in human experience prepares you for Jupiter. Nothing in the history of planetary science had prepared the scientists at JPL for what they were about to see. They thought they knew what was out there. They were wrong in the most spectacular way possible. Jupiter is not a planet in the way that Earth is a planet. It has no solid surface to stand on, no ground beneath your feet, no coastline or mountain range or desert plain. It is a world made almost entirely of gas, hydrogen and helium compressed by gravity into a roiling, churning, perpetually storming sphere 1,300 times the volume of Earth. Its atmosphere is a battlefield. Winds scream across its cloud bands at speeds of up to 500 kilometers per hour, sustained not for days or weeks but for centuries, possibly millennia, with no mountain range or ocean to slow them down. The colours alone, the creams and ochres and burnt oranges, the sudden dark slashes of storm systems larger than continents, were unlike anything in any photograph any human being had ever seen. Voyager sent back image after image, and at JPL the scientists stood in front of their screens in something very close to silence. And then there was the great red spot. You've probably seen photographs of it. That enormous oval storm sitting in Jupiter's southern hemisphere like a wound that refuses to heal. But photographs do not communicate scale the way numbers do, and numbers do not communicate it the way story does. The Great Red Spot is a storm that has been raging continuously for at least 350 years, since the first telescopes powerful enough to observe it were pointed at the sky in the 1600s. At the time Voyager flew past it, the storm was wide enough to swallow two Earths side by side. Its winds circulate at the edges at more than 400 kilometers per hour. It is not a storm in any sense that the word carries meaning on our world. It is a permanent feature of a planet, as fixed and enduring as a mountain range, and far more violent than anything our atmosphere has ever produced. Looking at Voyager's images of it, Something in the human mind quietly recalibrates what the word weather is allowed to mean. But Jupiter had a secret that no one expected. As Voyager 1 swung around the giant planet and its instruments scanned the moons below, one of the imaging scientists, a young researcher named Linda Morabito, noticed something strange in a photograph of Io, the innermost of Jupiter's large moons. There was an umbrella-shaped plume rising from Io's surface, a plume of material being ejected 280 kilometers above the ground. It was a volcanic eruption, an active volcanic eruption, happening in real time, captured by Voyager's cameras purely by chance. Io turned out to be the most volcanically active body in the entire solar system, more active than Earth, its surface perpetually resurfaced by hundreds of erupting volcanoes, driven by the gravitational squeezing of Jupiter's immense pull. No one had predicted this. No model had suggested it. The solar system had been hiding something extraordinary, and Voyager had simply flown past and seen it. That is what exploration does. It shows you that the universe is always stranger than your best guess. From Jupiter, Voyager 1 used the planet's enormous gravity as a slingshot, gaining speed and curving its trajectory towards Saturn. The journey between the two giants took approximately 19 months, and Saturn came into view in late 1980 with the same slow, building revelation that Jupiter had offered. But Saturn is a different kind of spectacle. Where Jupiter overwhelms you with violence and scale, Saturn does something more quietly astonishing. It offers you its rings. From a distance, those rings look like a flat disk surrounding the planet, elegant, geometric, almost architectural. Up close, as Voyager's cameras resolved them in detail no human instrument had ever achieved before, they revealed themselves to be something almost impossibly intricate. Thousands of individual ringlets, each made of billions of pieces of ice and rock ranging in size from a grain of sand to a house, moving in precise orbital paths around the planet. The rings are less than 1 kilometer thick in most places, yet they extend nearly 300,000 kilometers from the planet's center. If you scaled them to the size of a piece of paper, they would be thinner than the paper itself. They are one of the most beautiful structures in the known universe, and Voyager was the first human-made object to see them up close. Saturn also offered a moon that stopped everyone cold. Titan, the largest of Saturn's moons, is the only moon in the solar system with a thick atmosphere, a hazy, nitrogen-rich blanket of gas that completely obscures its surface from view. Voyager's cameras could not penetrate that haze, and the surface remained hidden. But the instruments detected something extraordinary. Complex organic molecules in Titan's atmosphere, the kind of chemistry that, on Earth, is associated with the building blocks of life. No one was ready to say the word life out loud, but everyone in the room was thinking it. Titan became, in that moment, one of the most compelling destinations in the solar system, a world whose secrets Voyager could tease but not reveal. That mystery would wait decades for another spacecraft to resolve it. Voyager 2, following its own trajectory, would go on to visit Uranus and Neptune, the first and still the only spacecraft to have done so. It found Uranus tilted entirely on its side, rotating like a rolling ball rather than a spinning top, for reasons that remain debated to this day. It found Neptune possessed of winds faster than any other planet in the solar system, winds screaming at 2,000 kilometers per hour through an atmosphere of deep, rich blue. It found Triton, Neptune's largest moon, orbiting the planet backwards, moving in the opposite direction of the planet's rotation, a fact so strange that astronomers are still working out what it means for the history of the outer solar system. Each world was its own revelation, each encounter a farewell, because Voyager would never return. There were no second visits on this itinerary. You looked, and then you moved on, and the planet shrank behind you into a point of light, and then into nothing at all. What strikes me most about this phase of the mission is not the science. Extraordinary as it was, it is the emotional mathematics of what was happening. Every image Voyager sent back was the last image of its kind. Every flyby was a first and final meeting between human technology and an alien world. The photographs of Neptune's cloud bands, of Uranus's pale blue serenity, of Saturn's rings catching the distant sunlight. These were not just data, they were goodbyes, and the people receiving them understood that. Each image was processed and printed and pinned to walls and passed around in corridors with a reverence that the engineers might not have named as reverence, but that is what it was. They were witnessing things that no human eye had ever witnessed, and they knew that no human eye might witness them again for a very long time. That knowledge made every image feel like a gift, and like all gifts given at the moment of departure, it carried with it the quiet, bittersweet weight of something ending. Carl Sagan had been thinking about a photograph for years. Not a photograph of a planet, not an image designed to collect data or test a hypothesis, but a portrait, a specific, deliberate, almost philosophical act of looking. His idea was simple and audacious in equal measure. Turn Voyager 1's cameras back toward the inner solar system and take a family photograph. Capture the Sun and as many planets as the camera could see from that unprecedented vantage point, 6 billion kilometers out. Show humanity what its home looked like from the edge of the solar system. Show the Earth not as a world, not as a landscape, not as a place of mountains and oceans and cities and civilizations, but as a pixel. A single, almost invisible point of light in a vast and indifferent darkness. NASA administrators were reluctant. The cameras had not been designed for this kind of imaging at this distance, and there was a real risk of damaging Voyager's instruments by pointing them too close to the Sun. The scientific value was, by any rigorous measure, essentially zero. But Sagan persisted, and eventually they said yes. On the 14th of February, 1990, Valentine's Day, which feels like it cannot be a coincidence, Voyager 1 turned its cameras toward home for the last time. The imaging sequence captured 60 frames, a mosaic of the solar system seen from the outside. And there, in one of those frames, suspended in a beam of scattered sunlight that crossed the camera's field of view at just the wrong angle to produce a kind of accidental halo, was Earth. It occupied less than a single pixel of the image, a pale blue dot. Those are the words Sagan would use, the words that became the title of his book, the words that have since become among the most quoted in the history of science writing. A mote of dust suspended in a sunbeam, that was us. That was everyone. That was every king and peasant, every act of courage and cruelty, every invention and war and love story and quiet ordinary afternoon that the human race had ever produced, compressed into a point of light so small you could cover it with the head of a pin. Sagan's response to that photograph was not triumphant. It was not the language of conquest or achievement. It was something far more measured and far more devastating. He wrote about it with a tenderness that has the quality of grief, not grief for something lost, but grief for something finally seen clearly for the first time. He wrote that our planet is a lonely speck in the great enveloping cosmic dark, that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. He wrote about the rivers of blood spilled by all those generals and emperors so that, in glory and triumph, they could become the momentary masters of a fraction of a dot. And then he wrote something that I find myself returning to again and again in the quiet hours of the night. Our planet is the only known home of life, at least for now. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. He was not being cruel. He was being honest in a way that very few people are brave enough to be. What made the pale blue dot photograph so extraordinary was not its technical quality. It was not a beautiful image in the conventional sense. No sweeping nebula, no jeweled ring system, no volcanic moon. It was grainy and distant, and the Earth itself was nearly impossible to see without someone pointing at it. What made it extraordinary was the shift in perspective it forced. Every other photograph of Earth from space had shown us a world, a sphere, recognizable, bounded, present. The famous Earthrise photograph taken by Apollo 8 astronauts in 1968 showed our planet rising above the lunar surface in vivid colour, blue and white and luminous against the black of space. It was beautiful, and it was humbling, but it still showed us a world you could imagine standing on. The pale blue dot showed us something else entirely. It showed us an address, a location in a universe that has no particular reason to notice us, and there is a terrifying clarity in that. The photograph arrived on Earth as digital data, a stream of ones and zeros transmitted across 6 billion kilometers of space at the speed of light, taking over 5 hours to complete the journey. Engineers at JPL converted that data into the image we now know, processing and assembling the 60 frames of the mosaic with painstaking care. When the final image appeared on their screens, the room was quiet for a long moment. People who had spent years working on the technical demands of the mission, the orbital mechanics, the power budgets, the instrument calibrations, found themselves looking at something that had nothing to do with any of that and everything to do with all of it. One of the scientists later described it as the moment the mission became real to her, in a way that all the data never quite had. The dot was not data, the dot was home. After the photograph was taken, Voyager's cameras were powered down for the last time. There was no reason to keep them running. They consumed power that was needed elsewhere, and there was nothing left ahead to photograph. The next star on Voyager's trajectory, a dim red dwarf called AC plus 79 3888, will not be reached for approximately 40,000 years. There was nothing to see. The cameras went dark, and Voyager continued outward, blind now, its only remaining purpose to keep its instruments alive and its signals singing homeward across the growing dark. In some ways, the powering down of the cameras was the first of many small silences, the first of many quiet closings that would, over the following decades, slowly reduce Voyager from a complex scientific observatory to a single stubborn transmitter, still talking, still reaching back across the void toward the pale blue dot it had last seen as a speck of light in a sunbeam. I think about that photograph often. I think about what it asked of the people who saw it. Not the scientists, not the engineers, but ordinary people who picked up Carl Sagan's book or saw the image reproduced in a magazine or a classroom poster and stopped for a moment in the middle of an ordinary day. It asked them to see themselves from the outside, to look at everything they had ever known, every city they had lived in, every person they had loved, every argument they had ever thought mattered deeply, and see it reduced to a point of light that could be covered by a grain of sand held at arm's length. And it asked them what they thought of that, what it meant, whether it made them feel small or somehow, in a way that is hard to articulate but that many people have tried, whether it made them feel something close to grateful. Grateful to be here at all. Grateful to be the kind of creature that can look at its own smallness and find it beautiful. There is a boundary around our solar system that has no walls, no markers, no visible edge of any kind. You could pass through it without feeling anything at all, no change in temperature, no shift in light, no sensation of crossing from one territory into another, and yet it is one of the most significant boundaries in the known universe, at least from the perspective of a small civilization on a pale blue dot trying to understand where it lives. It is the place where the sun's influence ends, where the great invisible breath that our star has been exhaling for 4.5 billion years finally runs out of momentum and stops, where the solar wind, that constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second, meets the interstellar medium and can go no further. Scientists call this boundary the heliopause, and for decades after Voyager's launch, no human-made object had ever crossed it. To understand what Voyager was moving through, in the long years after its planetary encounters, you need to understand what the solar wind actually is. The sun is not a quiet object. It is a thermonuclear furnace converting 4 million tons of hydrogen into helium every single second. And in doing so, it releases not just light and heat, but a continuous stream of energetic particles, electrons, protons, and the nuclei of helium atoms, that flow outward in all directions at speeds between 300 and 800 kilometers per second. This stream of particles is what we call the solar wind, and it does not stop at the orbit of Mars or Jupiter or even Neptune. It continues outward, growing thinner and slower as it spreads across an ever larger sphere of space, but it continues. It is the sun's presence felt across the entire solar system, and even beyond. The region of space filled by this solar wind, the bubble of the sun's influence, is called the heliosphere. And the heliosphere is enormous in a way that makes the distances between the planets feel almost cozy by comparison. By the time Voyager 1 had passed Neptune's orbit in 1989, it was already in a region of space that no instrument had ever directly sampled. The outer heliosphere is not empty. It is filled with the faint, tenuous presence of the solar wind, thinned almost to nothing by the vast distances it has travelled, and with energetic particles and magnetic fields that carry the sun's signature like a whisper heard from very far away. The spacecraft's instruments were measuring this environment continuously, sending back data that allowed scientists on Earth to begin building a picture of a region of our solar system that had existed, until then, only in theoretical models. And what they found, as Voyager crept outward year by year, was that the boundary they had predicted was real, but that the structure leading up to it was far more complex and surprising than anyone had anticipated. Here is the thing most people do not realize about the space between the planets. It is not nothing. We use the word vacuum, and we picture the kind of vacuum you might find in a sealed jar from which all the air has been removed, a perfect absence of matter. But the space of the outer solar system is filled with things. Cosmic rays stream through it from distant exploded stars, carrying energies that would be lethal to an unshielded human being in a matter of minutes. Dust particles, the remnants of comets and asteroids and collisions between rocky bodies, drift through it in quantities thin enough to be invisible, but thick enough to slowly erode any surface they encounter over geological time. Magnetic field lines stretch through it like invisible threads, channeling charged particles along paths that loop and curve across the entire solar system. And threading through all of it, like a river flowing through a landscape, is the solar wind. The outer solar system is not empty. It is a medium, a vast, cold, thin, extraordinarily complex medium through which Voyager was moving at 17 kilometers every second. The further Voyager traveled, the more the solar wind around it changed character. At a certain distance from the Sun, roughly 80 to 100 astronomical units out, where 1 astronomical unit is the distance from the Earth to the Sun, the solar wind undergoes a dramatic transition. It has been travelling outward so fast for so long that when it finally meets the resistance of the interstellar medium pressing inward from outside the heliosphere, it cannot accommodate the collision gradually. Instead, it slams into an invisible wall and slows down abruptly, becoming turbulent and heated and compressed. This region of shocked, slowed solar wind is called the heliosheath. It is chaotic in a way that the relatively smooth solar wind inside it is not. And Voyager 1 entered the heliosheath around 2004 at a distance of roughly 94 astronomical units from the Sun, approximately 14 billion kilometers. It was the first human-made object to reach this region. And what it found there was not what the models had predicted. The heliosheath turned out to be thicker and stranger than theorists had expected. Voyager spent years crossing it, its instruments recording a turbulent, magnetically complex environment where the direction of the magnetic field shifted unpredictably and the density of particles fluctuated in ways that did not match the existing models of how this region should behave. Scientists back on Earth were puzzled and delighted in equal measure. Puzzled because their models were wrong, delighted because wrong models mean new discoveries, and new discoveries are why you build spacecraft in the first place. The heliosheath was teaching them things about the outer boundary of our solar system that no amount of theoretical work from the inside could have revealed. You had to go there. You had to send something through it. And the only thing humanity had ever sent through it was Voyager. All of this time, through the long cruise past the planets, through the decades of slowly increasing distance, through the crossing of the heliosheath, Voyager's environment had one constant: the Sun. Faint, yes. Reduced to a star brighter than the others, but not incomparably so. But still present, still detectable, still sending its wind and its light and its magnetic signature outward to where Voyager was. The Sun was always there, in every measurement Voyager's instruments made, like a background note in a piece of music that you stop consciously hearing, but that structures everything around it. The entire heliosphere is, in a sense, the Sun's shadow, its presence projected outward into space in the form of charged particles and magnetic fields. And Voyager, for the first 35 years of its journey, had never left that shadow. It had never been anywhere the Sun did not reach. And then, one day in 2012, that changed. The solar wind around Voyager dropped to zero. The magnetic field changed direction abruptly and decisively. The density of particles from outside, cosmic rays from the galaxy beyond, surged dramatically. Voyager had crossed the heliopause. It had left the Sun's shadow entirely. For the first time in human history, something we had made was in interstellar space, truly between the stars, and it was still talking to us. In the summer of 2012, something happened at the edge of our solar system that scientists had been anticipating for decades, and yet was still not entirely prepared for when it arrived. The instruments aboard Voyager 1, instruments that had been running continuously for 35 years, through the flybys of the outer planets, through the long crossing of the Helios Heath, through distances that had grown so large that light itself needed more than 17 hours to cross them, began registering a change. Not a gradual change, not the kind of slow drift that you might expect at the edge of a boundary that had been defined theoretically for decades. A sharp change. An abrupt, decisive, unmistakable shift in the nature of the environment surrounding the spacecraft. The solar wind, which had been measured at varying levels for the entire duration of the mission, dropped to zero, and the number of cosmic rays streaming in from outside the solar system surged to levels the instruments had never recorded before. Voyager had crossed the heliopause. It had entered interstellar space. The confirmation did not come immediately. The data arrived on Earth and was analysed and debated and cross-checked with the careful, almost anxious thoroughness that characterises science at its most rigorous. The readings were unambiguous, but the scientific community wanted to be certain before making a claim that would be, by any measure, one of the most significant announcements in the history of space exploration. It took until September of 2012 for NASA to formally confirm what the data had been saying for months. Voyager 1 had become the first human-made object to leave the heliosphere and enter the space between the stars. The announcement was made at a press conference in Washington, and the scientists who delivered it did so with a composure that must have cost them something, because what they were describing was not a routine mission update. It was a threshold crossed that no one in the history of our species had ever crossed before. Here is what the heliopause actually is, and why crossing it matters so profoundly. The Sun, as I described in the previous chapter, exhales a constant stream of charged particles in all directions, the solar wind. This wind inflates the heliosphere, the bubble of the Sun's influence, against the pressure of the interstellar medium pushing in from outside. The interstellar medium is itself not empty. It is filled with the gas and dust and magnetic fields left behind by billions of years of stellar births and deaths, the accumulated residue of the galaxy's own long history. Where these two regions meet, where the Sun's outward pressure and the galaxy's inward pressure reach equilibrium, is the heliopause. It is not a wall, it is a membrane, a dynamic, fluctuating boundary that shifts in response to changes in solar activity, breathing in and out over millions of kilometers as the Sun's output rises and falls. But it is real, and it is sharp, and when Voyager crossed it, the instruments knew immediately. What lies on the other side of the heliopause is something that even now, more than a decade after Voyager first entered it, we are still only beginning to understand. The interstellar medium is colder and denser than the solar wind it presses against. Denser in the sense that its particles, though still extraordinarily sparse by any earthly standard, are packed more tightly than the thin, fast-moving solar wind that fills the heliosphere. The magnetic field in interstellar space runs in a different direction than the magnetic field inside the heliosphere, and this shift in direction was one of the clearest signals Voyager's instruments recorded as it crossed the boundary. Inside the heliosphere, the magnetic field lines are oriented one way, shaped and structured by the Sun's own rotation and the outward flow of the solar wind. Outside, they run along a different axis entirely, aligned with the broader galactic magnetic field, the vast and ancient structure of magnetism that threads through the entire Milky Way. The moment Voyager crossed the heliopause, it was no longer reading the Sun's magnetic signature. It was reading the galaxy's. There is something I find genuinely terrifying about that, in the quiet, contemplative way that the deepest facts about the universe tend to be terrifying. The Sun's magnetic field, the field that has shaped the environment of our entire solar system for 4.5 billion years, the field that deflects cosmic rays and structures the aurora and threads through every planet and moon and asteroid and comet in our local family, ends at the heliopause. It simply stops. On one side of that boundary, you're inside something the Sun has made, inside a bubble of influence that belongs, in some meaningful sense, to our star. On the other side, you're in a place the Sun does not reach, a place the Sun has never touched, in any direct physical sense, a place where the dominant magnetic signature is not our star's but the galaxy's own, the accumulated field of hundreds of billions of stars, shaped over timescales that dwarf the age of our solar system. Voyager crossed from one of those worlds into the other, and it is still in that second world now, moving deeper into it with every passing second. The scientists who had spent their careers preparing for this moment described their feelings afterward in ways that were consistently more emotional than you might expect from researchers discussing instrument readings. Edward Stone, Voyager's project scientist for more than 4 decades, spoke about the crossing with a quiet intensity that communicated something beyond professional satisfaction. He had spent the better part of his professional life waiting for this data, refining the models of what the boundary would look like, arguing with colleagues about where it would be and what Voyager would find when it crossed it. And when the data finally came in, what he described was not the satisfaction of being right. It was something more like awe. The universe had confirmed the prediction, yes, but the confirmation was so clean, so decisive, so dramatically unambiguous that it felt like the universe was making a statement rather than simply answering a question. Here is the edge, it seemed to say. Here's where one thing ends and another begins. You built something small enough to cross it and brave enough to keep transmitting. Now listen to what is on the other side. What Voyager found on the other side was a silence of a particular kind. Not the silence of emptiness. Interstellar space, as I mentioned, is not empty. But a silence in the sense of absence. The absence of the sun's wind. The absence of the sun's direct magnetic influence. The absence, for the first time in the entire mission, of the background hum of solar particles that had accompanied every measurement Voyager had ever made. In their place was something older and stranger, the whisper of the galaxy itself, the low-level radiation and magnetic fields and particle densities that have filled the space between the stars since long before our sun ignited. Voyager was reading a signal that predated our solar system. It was sampling an environment that existed before the Earth was formed, before the first ocean filled, before the first living cell divided in some warm, shallow pool 4 billion years ago. And it was sending that data home, across 23 billion kilometers of space, at 22 watts of power, to a handful of antenna dishes on a pale blue dot that the spacecraft had long since ceased to be able to see. The connection held, the signal came, and we listened. There is a question that almost every child asks at some point when they first learn about space, and it is a question that adults tend to dismiss too quickly because they think they already know the answer. The question is this: what does space sound like? And the answer that gets given, in classrooms, in documentaries, in the confident shorthand of popular science, is that space is silent. That sound cannot travel through a vacuum, that there is nothing out there to carry a wave, no medium to compress and expand, no air to vibrate against your eardrum. And this answer is true, as far as it goes. But it does not go nearly far enough. Because Voyager 1, drifting through interstellar space more than 23 billion kilometers from home, has been listening to something. And in 2017, scientists found a way to let the rest of us hear it too. The instrument responsible is called the Plasma Wave Science Instrument, and it has been part of Voyager's suite of sensors since launch. It does not detect sound in the way your ears do. It detects oscillations in the plasma that fills interstellar space, the faint vibrations of charged particles responding to disturbances in the medium around them. Plasma is not air. It does not carry sound waves the way the atmosphere does. But it does carry waves, electromagnetic waves, pressure waves, density variations that propagate through the medium in ways that are governed by the same underlying physics as acoustic waves in a gas. And when scientists at Cornell University took the data from Voyager's plasma wave instrument and converted the frequencies of those oscillations into the range of human hearing, essentially translating the language of plasma physics into audio, what came out of the speakers was not silence. It was a hum, a steady, low, continuous hum, like the sound of wind heard from inside a sealed room, or the noise a high-voltage power line makes on a quiet night. That was interstellar space. That was the sound of the medium between the stars. The tone itself is extraordinarily revealing to a physicist, even if to an untrained ear it sounds simply eerie. The frequency of plasma oscillations is directly related to the density of the plasma, how many charged particles exist in a given volume of space. Higher frequency means higher density. And the hum that Voyager recorded in interstellar space is at a higher frequency than the oscillations measured inside the heliosphere, which tells scientists that the interstellar medium is denser than the solar wind that fills the bubble of our solar system. Not denser in any way you could perceive directly. We're talking about a handful of particles per cubic centimetre, compared to a few tenths of a particle per cubic centimetre inside the heliosphere. By any earthly standard, both environments are as close to perfect vacuum as anything we can imagine. But the difference is measurable. Voyager measured it, and the measurement had a sound. What makes this data particularly valuable is not just the density reading it provides, but the fact that it gives scientists a continuous record of the interstellar medium's properties as Voyager moves through it. The spacecraft is not sitting still. It is travelling at roughly 60,000 kilometers per hour through a medium that is not uniform. There are regions of higher and lower density, areas where the interstellar plasma has been disturbed by events far away, by the shock waves of distant stellar explosions, by the magnetic turbulence of the galactic environment, by processes that scientists are still working to fully characterize. Each time the density changes, the frequency of Voyager's plasma hum shifts, and that shift is a data point, a measurement of the local environment at a specific location in interstellar space that no model and no Earth-based observation could provide. Voyager is not just listening to interstellar space, it is mapping it, one plasma oscillation at a time, as it drifts deeper into the dark. In 2020, the plasma wave instrument detected something unexpected, a faint, continuous signal that persisted for months, distinct from the oscillations associated with solar events. It was quieter than the bursts of plasma wave activity that Voyager had recorded when coronal mass ejections from the Sun sent shock waves racing outward through the heliosphere and into interstellar space. It had a different character, steadier, more uniform, more like background noise than a transient event. Scientists analysed it carefully and concluded that it represented the natural quiescent hum of the interstellar medium itself, the baseline song of the space between the stars, unperturbed by anything originating in our solar system. It was, in a meaningful sense, the quietest sound ever recorded, the background music of the galaxy, heard for the first time by an instrument that had been travelling for 43 years to reach a place quiet enough to detect it. I want you to think about what it took to hear that sound. Not just the engineering, the 43 years of continuous operation, the nuclear power source slowly fading, the antenna pointed homeward across 23 billion kilometres. Think about the human chain it required. The engineers in 1977 who designed the plasma wave instrument and made sure it would survive the journey. The scientists in the decades that followed who maintained the calibration of its sensors as the spacecraft aged and the environment around it changed. The researchers in 2020 who sat with the data and recognized that the faint, steady signal in their readings was not noise or instrument artifact, but something real, something the universe was actually saying. That chain of human attention, sustained across nearly half a century, is what made the sound audible. Without any single link in that chain, the hum of interstellar space would have passed through Voyager's sensors unheard, unrecorded, unknown. There is a quality to that hum that I find difficult to describe without reaching for language that scientists would rightly call imprecise. But we are not doing science right now. We are doing something else. Something that science makes possible but does not itself provide. We are trying to feel the weight of what Voyager has heard, and what it has heard, in that low and steady oscillation of interstellar plasma, is a voice that has been speaking since long before our Sun existed. The interstellar medium, the gas and dust and magnetic fields between the stars, is the material from which stars are born and into which they die. It is 4.5 billion years older than our solar system in this region of the galaxy, and it will still be here long after our Sun has expanded into a red giant and consumed the inner planets, and finally collapsed into a cooling white dwarf. The hum Voyager recorded is the hum of deep time, of a universe that was old before our world was young. And now consider what it means that we can hear it, that a civilization which has existed for the blink of a cosmic eye on a small rocky planet orbiting an ordinary star in the outer arm of a middling spiral galaxy managed to build something small and durable and clever enough to cross the boundary of its own solar system and hold a microphone, a plasma wave detector, which is the universe's version of a microphone, up to the space between the stars and record what it heard, and then send that recording home across a distance that takes light more than 22 hours to cross. That is not a routine achievement. That is not what you would expect from a species that has been doing science for only a few centuries, and spaceflight for only a few decades. That is something that should stop you in the middle of a quiet night and make you feel, however briefly, that the strange and improbable experiment of human consciousness might just be worth something after all. If you wanted to design a power source for a spacecraft that would travel beyond the reach of sunlight, beyond the orbit of every planet, beyond the boundary of the solar system itself, you would face a problem that has no elegant solution. Solar panels, the obvious choice for powering a spacecraft, are useless this far from the Sun. At the distance of Neptune, sunlight is already 900 times fainter than it is on Earth, barely enough to read by even on a cloudless day. At the distance Voyager has now reached, the Sun is simply one star among many. Its light arrives at Voyager's surface with essentially no usable energy. Solar panels of any practical size would generate nothing worth measuring. You need another source of power. You need something that will keep burning, quietly and steadily for decades, without any fuel supply, without any maintenance, without any human hand to tend it. The engineers who designed Voyager's power system found their answer not in chemistry or combustion, but in the slow, patient, unstoppable decay of radioactive matter. The device is called a radioisotope thermoelectric generator, and its operating principle is almost beautiful in its simplicity. Inside a sealed container, a quantity of plutonium-238, a radioactive isotope that decays by releasing alpha particles, undergoes continuous spontaneous decay. This decay releases heat. Not in bursts, not in reactions that need to be triggered or sustained, but constantly, inevitably, at a rate determined by the physics of the nucleus itself. The heat produced by that decay is then converted into electricity using an arrangement of thermocouples, devices that generate a voltage when one end is hot and the other is cold. Space provides the cold end for free. The plutonium provides the hot end. Between them, the thermocouple produces a small but steady current of electricity. No moving parts, no combustion, no fuel that needs to be replenished. Just the ancient energy locked inside atomic nuclei, releasing itself at a rate governed by the half-life of the material, the time it takes for half of the radioactive atoms to decay. Voyager 1 launched with 3 of these generators, collectively containing approximately 4.5 kilograms of plutonium-238. At launch, they produced a combined output of roughly 470 watts, about the same as leaving 4 moderately bright light bulbs on simultaneously. That does not sound like much, but it was enough to power all of Voyager's instruments, its computers, its transmitter, and the tape recorder that stored data before it could be downlinked to Earth. The system was lean, carefully designed, with no excess capacity and no wasted power. Every watt had a purpose, every circuit was justified, and the engineers who designed it understood from the beginning that the power budget would only get tighter with time, because plutonium-238 has a half-life of approximately 87.7 years. That means that every 87.7 years, half of the remaining plutonium atoms will have decayed, and the heat output, and therefore the electrical output, will have dropped by half. After nearly 50 years of continuous operation, Voyager's generators now produce roughly half the power they did at launch. The number today is somewhere around 230 watts, and it is falling by approximately 4 watts every year as more of the plutonium decays. 4 watts per year sounds trivial, but against a total budget of 230 watts, 4 watts per year is significant. It means that every few years the mission team at JPL must make decisions that would have been unthinkable in the mission's early days. Which instruments to turn off, which systems to sacrifice, which capabilities to permanently surrender in order to keep the remaining instruments alive for another year, another 2 years, another 5. These decisions are not made lightly. Each instrument that goes dark represents not just a loss of data, but the end of a scientific capability that cannot be restored. Once an instrument is off, it stays off. The power it consumed is redistributed to the systems that remain, and the spacecraft becomes, instrument by instrument, a little quieter. The history of these power-saving decisions is a chronicle of calculated loss. The plasma wave instrument's full waveform receiver was turned off years ago. The ultraviolet spectrometer went dark. The photopolarimeter subsystem was switched off. The cosmic ray subsystem operates in a reduced mode. Each shutdown was preceded by careful analysis and debate within the mission team, weighing the scientific value of the data the instrument was still producing against the power cost of keeping it alive, against the value of the instruments that would benefit from the freed up watts. It is, in a strange way, a process of triage. The spacecraft is aging, its resources are finite, and the people responsible for it must make choices that no amount of engineering ingenuity can avoid. They must decide what matters most. They must decide, in effect, what Voyager's last years will be spent doing. There is a layer of engineering complexity here that deserves a moment of attention because it speaks to the extraordinary care that has been invested in keeping this mission alive. Voyager's electronics were designed to operate within a specific temperature range. As the power output of the generators decreases, the amount of heat available to warm the spacecraft's interior also decreases, and in the cold of interstellar space, where temperatures in the surrounding environment hover close to minus 270 degrees Celsius, just a few degrees above absolute zero, keeping the electronics warm enough to function is not a trivial challenge. The mission team has had to redistribute heater power carefully, monitoring temperatures across the spacecraft's systems and making adjustments to prevent any critical component from cooling to the point of failure. This is not work that can be done by algorithm alone. It requires judgment, experience, and a deep familiarity with the specific quirks of a spacecraft that has been flying for nearly half a century. It requires people who know Voyager the way a doctor knows a long-term patient, and those people exist. There are engineers at JPL who have been working on Voyager for more than 30 years. There are mission scientists who have spent their entire careers analysing data from a spacecraft that launched before they were born. The institutional knowledge required to keep Voyager functioning, the understanding of which systems are fragile, which commands carry risks, which measurements are most scientifically valuable in the time that remains, is not written down in any single document. It lives in the minds of people who are themselves aging, people who will retire, and whose knowledge must be carefully transferred to younger colleagues before it is lost. In a very real sense, the race to keep Voyager transmitting is not just a race against the decay of plutonium. It is also a race against the decay of human memory, against the slow, inevitable loss of the expertise that has kept this mission alive through decades of challenges that no one anticipated when the spacecraft was designed. What I find most moving about all of this, the fading power, the turned-off instruments, the careful husbanding of every remaining watt, is that it transforms the engineering of Voyager's final years into something that feels almost like devotion. The people doing this work know that the mission is ending. They know the mathematics. They know that the power will eventually drop below the threshold required to operate any instrument at all, and that when it does, the signal will stop and will not start again. They are not working toward a moment of triumph or a dramatic discovery. They are working to extend the connection for as long as physics allows, to keep the line open, to ensure that when the last signal finally comes, it comes having carried as much data, as much science, as much of the universe's whispered secrets as it possibly could. That is not a job. That is something closer to a vigil. In the autumn of 2023, something went wrong with Voyager 1. Not the slow, predictable, mathematically inevitable decline of its power output that had been expected, planned for, managed with careful precision for decades. Something else. Something sudden and strange and deeply alarming to the small team of engineers at JPL who had dedicated their professional lives to keeping this spacecraft alive. The signal coming back from Voyager was still there, still crossing 24 billion kilometers of interstellar space, still arriving at the Deep Space Network antennas on schedule, still carrying the correct housekeeping data indicating that the spacecraft's systems were functioning. But the scientific and engineering data embedded within that signal had become pure gibberish, unreadable, corrupted, a stream of ones and zeros that made no sense by any interpretive framework the engineers applied to it. Voyager 1 was still talking, but for the first time in 46 years, no one could understand what it was saying. The problem, when it was eventually isolated after months of painstaking diagnostic work, turned out to reside in one of Voyager's 3 onboard computers, specifically in the flight data system, the computer responsible for packaging the spacecraft's scientific and engineering data into a format that could be transmitted home. A single chip in that computer had failed, and in failing it had corrupted the memory register that contained the instructions for how to format the data. The computer was still running. It was still receiving input from the spacecraft's instruments and attempting to process and transmit that data. But the instructions it was following were damaged, like a translator who has forgotten the rules of the language they are supposed to be translating into, still speaking, still producing sounds, but producing sounds that no longer correspond to meaning. The data flowing from Voyager's instruments was real. The transmission reaching Earth was real. But somewhere in between, in the corrupted memory of a decades-old computer chip more than 24 billion kilometers away, the translation was failing. Consider for a moment what the engineers were facing. They needed to diagnose a hardware failure on a spacecraft that no human being could visit, touch, open, or inspect. A spacecraft so far away that a signal sent at the speed of light takes 22.5 hours to arrive, and another 22.5 hours for any response to return. Every diagnostic test, every attempted fix, every question asked of the spacecraft had a turnaround time of 45 hours. If you sent a command on a Monday morning and it produced an unexpected result, you would not know until Wednesday morning, and then your next command, your response to that unexpected result, would not reach Voyager until Friday. The pace of troubleshooting was dictated not by the engineer's intelligence or preparation or dedication, but by the finite speed of light crossing an almost incomprehensible distance. There was no rushing it. There was no shortcut. There was only patience and precision and the willingness to work within constraints that would have broken a less devoted team. The diagnostic process took months. The engineers began by ruling out the most catastrophic possibilities: a complete failure of the flight data system computer, a problem with the transmitter itself, an issue with the deep space network antennas receiving the signal. One by one, through careful analysis of the corrupted data stream, they were able to establish that the spacecraft itself was healthy. The instruments were working, the power systems were functioning. The attitude control system, the system that keeps Voyager's antenna pointed toward Earth, was operating correctly. The problem was specifically and exclusively in the flight data system's memory, in a region of the computer's code that controlled the formatting of outgoing data. This was, in one sense, reassuring. A chip failure in one computer was a problem that might have a solution. A failure of the spacecraft's fundamental systems would not. The solution the engineers devised was elegant in its ingenuity and daunting in its execution. Since the corrupted memory chip could not be repaired, it was a physical hardware failure, not a software error that could be overwritten. The team needed to find a way to work around it. Their approach was to relocate the affected portion of the flight data system's code, the instructions for formatting outgoing data, to a different region of the computer's memory that was still functioning correctly. This sounds straightforward in principle. In practice, it was one of the most delicate software operations ever attempted on a spacecraft. The code in question had been written in the 1970s in an assembly language that almost no one still uses or fully understands. It had to be divided into sections that could fit into the available memory locations scattered across different parts of the computer, with each section carefully cross-referenced to ensure the whole would function correctly when reassembled. And every single step of this process had to be commanded from Earth, with a 45-hour round-trip delay on every test. On the 19th of April 2024, the engineers sent a command to Voyager that relocated the first section of the reworked code into its new memory location. Then they waited. 22.5 hours for the command to arrive, 22.5 hours for the response to return, 45 hours of silence during which there was nothing to do but continue the work of preparation and live with the uncertainty. When the response finally arrived, the engineers gathered around their monitors and read the data. It was clean, readable, correctly formatted. For the first time in 5 months, Voyager 1 was sending back data that made sense. The room at JPL, by all accounts, was not quiet at that moment. People who had maintained their composure through months of painstaking diagnostic work allowed themselves, briefly, to feel what they had been holding back. Relief is too small a word for what they felt. They had reached across 24 billion kilometers with a software patch and pulled their spacecraft back from the edge of permanent, irreversible silence. The remaining sections of the code were relocated over the following weeks, with equal care and equal patience. By the summer of 2024, Voyager 1 was fully restored, all 4 of its remaining active science instruments returning data correctly, the flight data system functioning as it had before the chip failure, the signal crossing interstellar space as faithfully as it had for 46 years. The crisis was over, the connection had held. But the episode left something behind in the minds of everyone who had followed it closely. a vivid and visceral reminder of how fragile the link between Voyager and Earth actually is. A single chip, a single region of memory in a computer running code written before most of the current mission team was born. That was all it took to bring the mission to the edge of silence. The spacecraft is extraordinary. The engineering that keeps it alive is extraordinary, but it is also old and tired, and held together by the knowledge and dedication of a small group of people working against the patient, inevitable pressures of time and entropy. What the 2023 crisis taught us, more than anything else, is that Voyager's survival has never been guaranteed. It has always been contingent on the continued functioning of aging hardware, on the availability of engineers who understand systems designed half a century ago, on the operational status of the deep space network antennas that receive its signal, on the slow decay of its power source staying above the threshold required to transmit. Every day that Voyager continues to communicate is, in a real sense, a small miracle. Not the miracle of divine intervention, but the miracle of human care applied consistently and intelligently over an almost incomprehensible span of time. The spacecraft has survived things it was never designed to survive. It has been fixed from distances that should have made fixing it impossible, and it is still out there, still transmitting, still sending its faint signal homeward across the dark. But the crisis reminded everyone listening that the silence, when it comes, may not announce itself in advance. It may simply arrive, one day, without warning. And the signal that was there yesterday will not be there tomorrow. There is something deeply human about the way we name things we care about. Ships get names, storms get names, telescopes and space stations and rovers on the surface of distant planets get names. And the instruments aboard Voyager 1, the sensors and detectors and measuring devices that have been its eyes and ears and nervous system for nearly half a century, have names too. The Plasma Wave Science Instrument, the Magnetometer, the Low Energy Charged Particle Instrument, the Cosmic Ray Subsystem. These names are functional, descriptive, carrying within them the plain language of engineering rather than the poetry of exploration. But to the people who have spent their careers listening to the data these instruments produce, they are something more than labels. They are personalities. They are the specific ways in which Voyager experiences its environment, and one by one, over the years and decades, those instruments have been going dark. At launch, Voyager 1 carried 11 distinct scientific instruments. Each one had been designed, argued for, competed over, and finally selected through a process that took years, and involved hundreds of scientists submitting proposals and defending their cases before review committees. Each instrument represented a scientific question, something specific that humanity wanted to know about the outer solar system and the space beyond it. The imaging science system wanted to see. The infrared interferometer spectrometer and radiometer wanted to measure heat. The photopolarimeter wanted to study light scattered by particles and surfaces. The ultraviolet spectrometer wanted to probe the chemistry of planetary atmospheres. Together they formed a suite of senses far more acute than anything a human explorer could carry, designed to perceive a universe that our own unaided biology can barely detect. By the time Voyager crossed the heliopause in 2012, most of those original 11 instruments had already been switched off. The imaging system, the cameras that had sent back those extraordinary photographs of Jupiter's moons and Saturn's rings and the pale blue dot, had been powered down in 1990, immediately after the family portrait of the solar system was taken. There was nothing left ahead worth photographing, and the cameras consumed power that was needed elsewhere. The infrared spectrometer had been turned off. The photopolarimeter had gone dark. The ultraviolet spectrometer, which had done such valuable work studying the atmospheres of the outer planets, was no longer running. Each shutdown had been a calculation, a weighing of what the instrument could still contribute against what its power consumption was costing the instruments that remained. And each time the calculation came out the wrong way for an instrument, it was switched off and stayed off. 4 instruments remain active on Voyager 1 today. 4 out of the original 11. The Plasma Wave Science Instrument, which detects oscillations in the plasma of interstellar space and produced that extraordinary hum I described earlier. The Magnetometer, which measures the direction and strength of the magnetic field in Voyager's immediate environment. The instrument that confirmed, more decisively than any other, that the spacecraft had crossed the heliopause and entered interstellar space, where the galactic magnetic field dominates. The Low Energy Charged Particle Instrument, which detects and counts the charged particles streaming through the spacecraft's location, cosmic rays from the galaxy, and the last remnants of the solar wind that no longer reach this far, and the cosmic ray subsystem, which measures the highest energy particles in Voyager's environment, the most energetic messengers from supernovae and other cataclysmic stellar events scattered across the Milky Way. 4 instruments, 4 specific ways of sensing a place no human has ever been, and no human will visit for tens of thousands of years. What these 4 instruments are telling us, collectively, is a story about the nature of interstellar space that we could not have obtained any other way. The magnetometer data shows the structure and direction of the galactic magnetic field at Voyager's specific location, revealing how it varies over the distances the spacecraft has travelled since crossing the heliopause. The plasma wave instrument continues to record the density fluctuations of interstellar plasma, building a profile of the medium between the stars that grows more detailed with every passing month. The charged particle instruments count the cosmic rays streaming through Voyager's position, rays that were partially blocked by the Sun's magnetic field while the spacecraft was inside the heliosphere, and that now arrive unimpeded, carrying information about their sources across distances of hundreds or thousands of light years. Together, these 4 instruments are producing the only direct in situ measurements of interstellar space ever made. There is no other source for this data. There is no substitute. When Voyager stops transmitting, this stream of information will stop with it, and will not resume until another spacecraft, if one is ever sent, reaches the same region of space. The power required to run these 4 instruments is carefully managed down to the level of individual watts. The mission team has developed detailed models of Voyager's power consumption, tracking exactly how much electricity each system draws, and adjusting the distribution of available power as the RTGs continue their slow decline. Heaters that once kept certain components warm have been turned off, a calculated risk, accepting that those components may be damaged by the cold in exchange for the watts they would have consumed. The onboard tape recorder, which in the mission's early days stored data for later transmission during deep space network contact windows, has been removed from regular use to conserve both power and the mechanical wear on its components. Every decision is a trade-off. Every watt saved somewhere is a watt available somewhere else, and the somewhere else always is the 4 instruments still awake and still listening. The timeline for future shutdowns has been projected with painful precision. Sometime around 2025, the mission team expects to need to turn off another instrument or subsystem to keep the remaining ones alive. By 2030, the power situation will have deteriorated to the point where operating even a single science instrument will require careful management of every other system on the spacecraft. The projections beyond 2030 become increasingly uncertain, because the behaviour of aging hardware in the environment of interstellar space is not perfectly predictable. A component might fail unexpectedly, or might survive longer than the models suggest. But the broad trajectory is not in doubt. The power curve slopes downward with mathematical certainty, and at some point along that curve, the last instrument will consume more power than the RTGs can supply. At that point, Voyager will have nothing left to say. What I find myself thinking about in the quiet of considering these final years is not the instruments themselves, but the questions they are still answering. Every day that the plasma wave instrument runs, it adds another data point to humanity's understanding of the space between the stars. Every day the magnetometer reports the direction of the galactic magnetic field at Voyager's location. It extends a map that no one has ever been able to draw before. These are not trivial contributions made in the twilight of a dying mission. They are genuinely irreplaceable observations, made from a position in space that cost nearly 50 years of continuous effort to reach. The instruments that are still awake tonight are doing work that matters. They are answering questions that could not be answered any other way. And when they finally go dark, one by one, or perhaps all at once, depending on how the power curve falls, those questions will have been answered as completely as Voyager could answer them. The rest will have to wait for whoever comes next. There is a particular kind of knowledge that is harder to hold than ignorance. Ignorance is formless. It has no edges, no specific weight, no moment you can point to and say, there, that is when it ends. But knowledge of an ending is different. Knowledge of an ending has a shape, it has a timeline, it has numbers attached to it, and numbers have a way of making abstract futures feel suddenly, uncomfortably real. The engineers and scientists who work on Voyager 1 carry this kind of knowledge every day. They know, with a precision that leaves very little room for hope or uncertainty, approximately when the mission will end. Not the year of some unexpected catastrophic failure that could happen at any time and cannot be predicted, but the year when the physics of radioactive decay will have reduced Voyager's power output to a level that can no longer sustain any scientific instrument, any meaningful transmission, any connection across the dark. That year is not far away. And the mathematics that leads to it is ruthless in its clarity. Let me walk you through those numbers slowly, because they deserve to be felt rather than merely stated. Voyager's radioisotope thermoelectric generators currently produce approximately 220 to 230 watts of electrical power, declining by roughly 4 watts per year as the plutonium-238 continues its slow decay. 4 watts per year does not sound catastrophic, but consider what it means cumulatively. In 5 years, the available power will have dropped by 20 watts, in 10 years by 40 watts. Against a budget of 230 watts, that represents a reduction of nearly 20% over a single decade, 20% fewer watts to distribute among a spacecraft's computers, heaters, transmitter, and scientific instruments. Each reduction forces a choice. Each watt lost somewhere must be compensated for by turning something off somewhere else, and there are fewer and fewer somethings left to turn off. The transmitter that sends Voyager's signal home is itself one of the largest consumers of power on the spacecraft. It operates at approximately 22 watts, a number that has not changed significantly over the mission's lifetime, because the transmitter either works or it does not, and reducing its power would weaken the already extraordinarily faint signal to the point where Earth's antennas could no longer detect it. The transmitter is, in a sense, the last thing that will be sacrificed. It is the voice of the mission. As long as the transmitter runs and the antenna remains pointed homeward, and the deep space network antennas on Earth remain operational and sensitive enough to detect the signal, there is a connection. The moment the transmitter loses power, the connection ends, and the mathematics of the power curve suggests that this moment will arrive sometime in the late 2020s, possibly extending into the very early 2030s if conditions are favourable, and if the mission team's careful power management continues to succeed. What does it mean, in practical terms, that the silence is this close? It means that the people working on Voyager today are not working toward a distant theoretical future event. They are working towards something that some of them will witness within their professional lifetimes, possibly within the next 5 to 10 years. The junior engineers joining the Voyager team today may be there when the last signal arrives. The senior scientists who have dedicated decades to the mission are almost certainly going to be alive when it ends. This changes the emotional texture of the work in ways that are difficult to articulate but easy to understand. You're not maintaining an ongoing mission with an open-ended future. You're tending something in its final years, extracting every possible piece of value from its remaining time and preparing, however you prepare for such a thing, for the moment when the work you have been doing is finished in the most absolute sense possible. The final silence will not be a single moment in the way that a power switch being thrown is a single moment. It will be a process, a gradual fading rather than an abrupt cut-off. As the power drops below critical thresholds, instruments will go dark one by one. We have already discussed that process, and it is already underway. The computers that manage the spacecraft's attitude control and data processing will eventually be running on so little power that their operation becomes unreliable. The heaters that keep critical components above their minimum operating temperatures will be reduced and finally eliminated, and as components cool below their functional limits, they will stop working correctly. The transmitter itself, running on whatever power remains after everything else has been stripped away, will eventually receive insufficient voltage to maintain its output frequency and power level. Its signal will weaken, its frequency may drift, and at some point, the deep space network antennas, which are already operating at the very edge of their sensitivity to detect Voyager's signal, will no longer be able to distinguish it from the background noise of the universe. That is when, from Earth's perspective, the silence will arrive. There is something I want you to understand about the moment that signal disappears from the antennas. It will not mean that Voyager has stopped moving. The spacecraft will continue on its trajectory through interstellar space, indifferent to the loss of its own voice, for billions of years after its transmitter goes cold. It will pass within a few light years of other stars. It will drift through regions of the galaxy that no human mind has mapped. It will continue to carry, sealed in its golden record, the sounds and images of a civilization that will have changed beyond recognition by the time any of this happens. But from our perspective, and from the perspective of everyone on Earth who's been listening, the silence will be total and permanent. We will know where Voyager is, because we can calculate its trajectory with precision. We will know what it is passing through, but we will not be able to hear it. The conversation, after nearly 50 years, will simply be over. What troubles me most about this, in the slow hours of a contemplative night, is not the loss of the science, though the loss of the science is real and significant. What troubles me is the nature of the asymmetry. Voyager will still be there, moving through interstellar space, long after we have lost contact. It will still be carrying the golden record. It will still be, in whatever sense a machine can be said to be anything, present in the universe. But we will have no way of knowing it. We will have no way of confirming that it has not been struck by some interstellar debris, no way of verifying that its structure remains intact, no way of receiving any signal from the environment it is moving through. The link will be broken on our end, not Voyager's. And that broken link, the silence on the receiver rather than the transmitter, has a quality of loss that is almost impossible to fully process. It is not death, exactly. It is something stranger. It is the end of listening. The end of the relationship between the made thing and its makers, and that end, the mathematics tells us with its usual indifference to human feeling, is very nearly here. Once the signal stops, once the transmitter goes cold and the last data packet completes its 22-hour journey across interstellar space and arrives at our antennas for the final time, Voyager 1 will become something different, not broken, not destroyed, not lost in any meaningful sense, because its position and trajectory can be calculated with precision for millennia to come. It will simply become unreachable. An artifact drifting through interstellar space on a trajectory that was determined by the physics of its launch and its planetary flybys nearly 50 years ago, unchangeable now by any human intention, carrying forward into a future so remote that the numbers required to describe it stop feeling like numbers and start feeling like philosophy. To understand where Voyager is going and what will happen to it on the timescales that interstellar travel demands, you need to let go of every intuition you have built up through a lifetime of experiencing time as something that moves at a human pace. Right now, tonight, Voyager 1 is travelling at approximately 17 kilometers per second relative to the Sun. This sounds fast, and by any standard relevant to human experience, it is extraordinary. 17 kilometers per second is roughly 60,000 kilometers per hour, or about 55 times faster than a commercial aircraft at cruising speed. If you could travel at Voyager's speed, you could circle the Earth in less than 40 minutes. You could reach the Moon in about 6.5 hours. These are genuinely impressive numbers, and the engineering that produced them, the gravitational slingshots around Jupiter and Saturn that gave Voyager its final velocity, represents one of the most elegant pieces of trajectory mathematics ever executed. And yet, against the distances of interstellar space, 17 kilometers per second is heartbreakingly slow. It is the pace of something that will take not years but tens of thousands of years to reach even the nearest stars. In approximately 40,000 years from now, Voyager 1 will make its closest approach to another star system. The star in question is a dim red dwarf called Gliese 966, also known in some catalogues by its designation AC plus 793888. It is an unremarkable star by most measures, cooler and smaller than our Sun, the kind of star that rarely appears in popular accounts of stellar astronomy. Voyager will not enter its system. It will not come anywhere close enough to be captured by its gravity or to have its trajectory meaningfully altered. At its closest approach, it will pass within approximately 1.7 light-years of this star, roughly 100,000 times the distance from the Earth to the Sun. From that star's perspective, Voyager will be a ghost, a speck of metal and glass passing silently through the outer reaches of its neighbourhood, invisible to any observer without extraordinary instruments, leaving no trace of its passage, and then it will continue moving into the deeper dark beyond. In 1,000,000 years, a span of time so vast that it swallows the entire history of our species many times over, Voyager will have travelled approximately 300 light-years from the Sun. 300 light-years in a galaxy that is 100,000 light-years across, and contains somewhere between 200 and 400 billion stars. 300 light-years is not a large distance on the scale of the Milky Way. It is a short walk in a city the size of a continent. But it is enough to place Voyager in a region of space that is completely unrelated to any landmark of our solar neighbourhood, surrounded by stars that no human astronomer has yet studied in detail, moving through an interstellar medium whose local properties are unknown to us. In a million years, Voyager will be in genuinely uncharted territory. Uncharted not because we have not looked, but because no instrument we have built or could build in the foreseeable future is capable of observing it directly at that distance. What will Voyager look like in a million years? The golden record will still be there, sealed in its aluminum jacket protected from the erosion of interstellar dust by the spacecraft's body, carrying its encoded sounds and images in a format that a sufficiently advanced civilization could, in principle, still decode. The aluminum and titanium structures of the spacecraft itself will be largely intact. Metals that rust and corrode on Earth, where oxygen and water do their patient work, are effectively immune to degradation in the vacuum of interstellar space. The high-gain antenna, the instrument boom, the RTG power system, cold now, silent, no longer producing heat or electricity, will all still be there. Physical artifacts of a civilization that existed on a small rocky planet circling an ordinary star in the Orion arm of the Milky Way. In a million years, Voyager will be a fossil, a perfectly preserved fossil, drifting through space at the same velocity it carries tonight, carrying the last physical traces of a moment in Earth's history that will be as remote to whatever humans or their descendants may be by then, as the first stone tools are to us now. In 5 billion years, the approximate remaining lifetime of our Sun before it expands into a red giant and eventually collapses, Voyager will be somewhere between 5,000 and 10,000 light-years from the solar system, depending on the subtle gravitational perturbations it experiences as it passes through regions of varying stellar density over geological timescales. The Sun will be dead. The Earth will have been consumed. Whatever our civilization has become, if it has survived, if it has expanded beyond this solar system, if it persists in any form recognizable to us tonight, will have had 5 billion years to evolve beyond anything we can imagine. And Voyager will still be moving, still carrying its golden record, still following the trajectory that was determined on a summer morning in 1977 when a Titan rocket ignited above a Florida launch pad and a small golden machine began its journey toward the stars. There is a terrifying beauty in this trajectory that I find myself returning to in quiet moments. We did not plan for Voyager to become an eternal artifact. The mission was designed around a 5-year science program, a grand tour of the outer planets, a collection of photographs and measurements. The fact that it has lasted nearly 50 years is already far beyond what was designed for. The fact that it will continue travelling through the galaxy for billions of years after its last signal fades is not an engineering achievement, but a consequence of physics. Once something is moving in the near vacuum of interstellar space with no significant gravitational influence to alter its path or friction to slow it down, it simply keeps moving. Forever, or as close to forever as anything in this universe gets. Voyager will outlast the people who built it by billions of years. It will outlast the civilization that built it. Almost certainly, it will outlast the Sun. And in that extraordinary longevity, that accidental immortality granted by the physics of empty space, there is something that feels like a message, not the one encoded on the golden record, but a different message, written not in sounds and images, but in the simple fact of continued motion. We were here. We reached this far, and whatever comes next, this small piece of us will keep going. Imagine being asked to represent your entire species in a single object. Not your country, not your culture, not your generation, your species. Every human being who has ever lived, and every human being who will ever live, compressed into something small enough to attach to a spacecraft and send into the void between the stars. Imagine being told that this object might be found by another civilization, or it might drift through interstellar space for billions of years without ever being touched by any hand, seen by any eye, or decoded by any mind. Imagine knowing, as you make your selections, that the probability of the latter outcome is vastly higher than the probability of the former, and then imagine making those selections anyway, with the same seriousness and care as if discovery were certain. This is what Carl Sagan and his committee did in the spring and summer of 1977. They made a message for silence, and the result was one of the most extraordinary objects ever created by human hands. The Golden Record is a 12-inch gold-plated copper disc, visually similar to the vinyl records that were the dominant music format of the era. On its surface are encoded in analog form 115 images, diagrams, photographs, and technical illustrations selected to convey as much information as possible about the nature of Earth and its inhabitants to a recipient with no prior knowledge of either. The images begin with the most fundamental things: mathematical definitions, the structure of the DNA molecule, the anatomy of a human being, the stages of human development from conception to old age. They progress through images of our planet, continents and oceans, forests and deserts, the structures of weather systems seen from space. They show animals and plants, geological formations, and the works of human civilization, houses and cities and highways and ships, and they show people eating, people running, people laughing, a mother nursing a child, a group of children at schoolyard, an old man with a weathered face looking quietly into the camera. These are not the images of a civilization trying to impress. They are the images of a civilization trying to be honest. Alongside the images, the record carries sounds, 90 minutes of music, selected from across human cultures and across history with an ambition that bordered on the impossible. Bach's Brandenburg Concerto No. 2 in F major, Mozart's The Magic Flute, Beethoven's String Quartet No. 13 in B flat, Chuck Berry's Johnny B. Good, a selection that prompted the physicist Philip Morrison to remark, only half jokingly, that it was premature to send rock and roll to the stars, a Senegalese percussion piece, a Navajo night chant, a Pygmy girl's initiation song, a Peruvian wedding song, an Australian Aboriginal song, Georgian choral music, Japanese court music more than 1,000 years old. The selection was not comprehensive. No selection of 90 minutes could be comprehensive. But it was made with genuine care and a real desire to represent not just the Western classical tradition, but the full breadth of human musical expression across cultures and centuries. It is imperfect, as all human choices are imperfect, but it is earnest, and earnestness, in the face of the void, counts for something. The record also carries greetings, 55 greetings in 55 languages, ranging from Akkadian, an ancient Semitic language spoken in Mesopotamia more than 4,000 years ago and now extinct, to Wu Chinese, to English, to Amoy, to Welsh. The English greeting, spoken by the then 6-year-old son of one of the project scientists, says simply, "Hello from the children of planet Earth." It is a child's voice, crossing billions of kilometers of empty space, addressed to an audience that may not exist, in a universe that has given us no particular reason to believe anyone is listening. And yet there it is. Hello from the children of planet Earth. There is no sentence in the history of space exploration that carries more weight in fewer words. No transmission that compresses more of what we are, curious, hopeful, small, reaching, into a simpler form. The record's cover is an aluminum jacket etched with instructions for how to play it back. These instructions are encoded in the language of pulsars. The precise periods of 14 known pulsars are marked, providing any finder with both a map of the solar system's location relative to these cosmic lighthouses and a set of reference frequencies that can be used to calibrate the playback speed. The cover also shows a diagram of a hydrogen atom in two energy states. The transition between these states produces a radio frequency that is, in the literal sense, universal, the same everywhere in the cosmos, which encodes the correct playback speed and the timescale of the encoded images. The people who designed these instructions spent months debating whether they were genuinely decipherable by a civilization with no prior knowledge of human conventions. They consulted linguists and information theorists and astronomers. They tested the instructions on colleagues who had not been involved in their design, asking them to decode the playback procedure from scratch. It was as rigorous a process of communication design as anything in the history of human language. And at the end of it, they were still not certain it would work. They sent it anyway. Here is the thing most people do not fully reckon with when they think about the Golden Record. It was made with the full understanding that it would almost certainly never be found. The scientists involved knew the mathematics of interstellar space. They knew that Voyager's trajectory was not aimed at any specific star system, that the distances involved were so vast that the probability of any civilization encountering the spacecraft by chance, in the billions of years it will travel, is extraordinarily small. Carl Sagan himself acknowledged this. He described the record not as a serious attempt at communication, but as a message in a bottle cast into the cosmic ocean. Knowing that the ocean is very large and the bottle is very small, but casting it anyway because the act of casting it says something important about who you are. It says that you are the kind of civilization that believes contact is possible, that believes other minds might exist in the universe, that believes the universe is worth addressing, even from the profound uncertainty of not knowing whether anyone is home to receive the address. And I think that is what moves me most deeply about the Golden Record, not its contents, extraordinary as they are, but the psychological state it required to make it. To make the Golden Record, you had to believe simultaneously that the gesture was almost certainly futile, and that it was worth making anyway. You had to hold both of those things in your mind at the same time and choose in full knowledge of the futility to make the gesture. That is not the posture of optimism exactly. It is something more nuanced and more interesting, a kind of defiant meaning-making in the face of cosmic indifference, a refusal to let the silence of the universe become an excuse for your own silence, a decision that even if no one ever hears the Pygmy Girl's initiation song, or the child's voice saying hello from the children of planet Earth, the act of recording them and sending them outward mattered. Not because it will be received, but because it was sent. Because we are the kind of creature that sends things into the dark and then stands at the edge of the darkness and listens for an answer, even knowing the answer may never come. There is a building in Pasadena, California, that does not look like the kind of place where history is made. It is a low, functional structure on the campus of the Jet Propulsion Laboratory, full of monitors and workstations and the particular quality of institutional quiet that settles over places where serious, sustained attention is the primary activity. The people who work there do not wear spacesuits. They do not experience weightlessness or radiation, or the vertigo of orbital flight. They sit at desks, they write code and analyze data, and attend meetings and drink coffee from paper cups. And they maintain, through the daily practice of that ordinary professional life, a connection to something that is neither ordinary nor especially proximate to daily life. A spacecraft drifting through interstellar space, more than 23 billion kilometers away, still sending home its faint and faithful signal, still needing someone on the other end of the line to be listening when it arrives. Edward Stone joined the Voyager project in 1972, 5 years before launch, and served as its chief scientist for 50 years, a tenure so long that it spans the entire professional lifetime of most researchers working today. He was there when the first images of Jupiter's moons came back. He was there when Saturn's rings were resolved in detail that no telescope had ever achieved. He was there in 2012 when the data confirmed that Voyager had crossed the heliopause and entered interstellar space. And he was there in 2022 when he finally stepped back from the role he had occupied for half a century. 50 years. Most scientific careers do not last that long in total. Stone's association with a single spacecraft spanned the entire arc of what most people call a working life. Ask him what kept him engaged for 50 years, and the answer he gives is not complicated. The universe, he says, keeps surprising you. Every time you think you understand what Voyager is going to find, it finds something else, something better, something that requires you to revise everything you thought you knew. How do you walk away from that? The engineers who have worked on Voyager's operations, as distinct from its science, carry a different kind of relationship to the mission, one that is less about discovery and more about devotion. These are the men and women who understand, at the level of individual circuits and software registers and antenna pointing angles, exactly how the spacecraft works. They know which components run warm and which run cold. They know the history of every anomaly the spacecraft has experienced, what caused it, how it was resolved, and what it suggests about the health of the systems that remain. They know, in a way that no manual fully captures, the personality of the machine, its quirks, its tendencies, its responses to commands that differ subtly from what the textbook would predict. This knowledge has been accumulated over decades of daily attention, and it lives not in any document, but in the minds of the people who have been paying that attention. One of the consequences of this is that the transfer of institutional knowledge has become one of the most critical challenges facing the Voyager mission in its final years. The engineers who know the spacecraft most deeply are, in many cases, approaching the end of their own careers. Some have already retired. Others are in their 60s and 70s, with the kind of accumulated expertise that takes decades to build and cannot be transferred quickly or completely to younger colleagues. JPL has been actively working on this problem, bringing in new engineers, having them work alongside the veterans, documenting systems and procedures in greater detail than was thought necessary when the people who understood them were still reliably present. But institutional knowledge is not just information. It is judgment, the ability to look at an anomalous reading and know, from decades of experience, whether it represents a real problem or a known quirk of an aging sensor. That judgment cannot be fully written down. It can only be partially transferred, imperfectly inherited, and inevitably diminished with each generation of handoff. The emotional dimension of the work is something that the people involved discuss with a candour that is unusual in the culture of engineering. These are not people who are given to sentimentality as a professional posture. The training and the culture of aerospace engineering selects for precision and rigour and a certain emotional economy in the face of complex problems. And yet, when they talk about Voyager, something else comes through. Something that the language of engineering does not quite have words for. One veteran mission controller, when asked what it feels like to know the mission is ending, said that it felt like watching a very old friend prepare to leave on a journey from which they will not return. You know it is coming. You have known for years. But the knowing does not make the feeling smaller when the time actually approaches. It just makes it more familiar. And familiarity in this context is its own kind of grief. The Deep Space Network operators who actually receive Voyager's signal form another layer of this human story. The network consists of 3 complexes of large antenna dishes, one in Goldstone, California, one outside Madrid in Spain, and one near Canberra in Australia, positioned around the globe so that at least one complex always has a line of sight to any spacecraft in deep space, regardless of the Earth's rotation. The dishes are enormous, the largest are 70 meters in diameter, the size of a football stadium lying on its side, and they are sensitive to a degree that strains the imagination. They must detect a signal of 22 watts arriving from 23 billion kilometers away, a signal so weak by the time it reaches Earth that it carries less power than the light from a single firefly seen from several kilometers away. The operators who run these dishes do not think of themselves, for the most part, as participants in a story of historic proportions. They think of themselves as doing their jobs, but their jobs, in the case of Voyager, have connected them to one of the longest-running acts of listening in human history. What I keep returning to when I think about all these people, the scientists, the engineers, the antenna operators, the mission controllers, is the quality of attention they have brought to this work over nearly 5 decades. Sustained, careful, expert attention directed at a machine more than 20 billion kilometers away. Attention that has navigated hardware failures and software corruptions and budget cuts and the ordinary disruptions of institutional life. Attention that has been maintained across the retirements and deaths of colleagues, across changes in technology that have made some of the original systems obsolete and required their replacement with equipment that did not exist when the mission was designed. The attention itself is a kind of achievement, separate from and as significant as anything the science has revealed. It is proof that human beings are capable of caring about something for a very long time, of showing up year after year to maintain a connection that most of the world has forgotten exists, and now that connection is nearing its end. The people who have tended it, who have spent careers and in some cases entire working lives in service of this faint signal crossing interstellar space, are preparing, in whatever way one prepares for such a thing, for the silence that is coming. Some of them will be there when it arrives. Some will have retired by then, learning the news from a distance, the way you learn about the death of someone you once knew well but have not seen in years. The grief, in either case, will be real. Because what they will have lost is not just a mission or a data stream or a professional responsibility. They will have lost a relationship. The particular, irreplaceable relationship between a maker and a made thing, sustained across 50 years and 23 billion kilometers against every reasonable expectation of survival. That relationship has been one of the most remarkable things our civilization has ever managed to sustain. And when the signal finally fades, the silence will not just be out there among the stars. It will be felt here, in the quiet rooms where people have spent their lives listening. Let me ask you something. In the quiet of this hour, as the darkness settles around you and your breathing slows and the world outside shrinks to something manageable and distant. What does it mean when a voice goes silent? Not when a conversation ends by mutual agreement, not when both parties say goodbye and put down the phone and go on with their separate lives, but when one voice simply stops, mid-sentence or mid-breath, without ceremony, without announcement, without the dignity of a prepared farewell. That kind of silence is different. It has a different weight. It asks a different question of the people left listening, and that is the silence that is coming for Voyager 1. Not a planned shutdown, not a deliberate powering down, not a ceremony with speeches and commemorations, though there will certainly be articles written and tributes paid. The actual moment of ending will be quieter than that. A signal that was there will no longer be there, and the universe will not pause to mark the occasion. I have been thinking about what the last signal will actually look like, from the perspective of the engineers and scientists at JPL who will be monitoring it. It will not look dramatic. It will look like what it is: data. A stream of numbers representing housekeeping information from Voyager's systems. Power levels, temperatures, the status of its remaining instruments, the attitude of its antenna relative to Earth. These numbers will have been declining in various ways for years before the final transmission. Power readings getting lower, temperatures approaching dangerous thresholds, instrument outputs showing the reduced sensitivity of aging sensors. The last signal will be one more point on a trend that has been visible for a long time. It will differ from the second to last signal in no spectacular way. And then, at some point, the trend will reach its end point. The power will drop below the threshold required to sustain the transmitter. The signal will stop, and what the engineers will see on their monitors is not a dramatic flatline, but simply the absence of something that was previously present. The data stream will end, the frequency will be empty, Voyager will still be there, 23 billion kilometers away, still moving, still carrying its golden record. But it will no longer be speaking. The last signal will travel at the speed of light from wherever Voyager is when it transmits, crossing the interstellar medium and the heliosphere and the inner solar system, taking more than 22 hours to complete the journey. During those 22 hours, the engineers on Earth will not yet know that the signal they are waiting for is the last one. They will be waiting in the ordinary way, monitoring the frequency, preparing to receive the data, doing the routine work of a mission that has been routine for decades, and then the signal will arrive. It will be processed, its content will be recorded, and sometime after that, perhaps hours later, perhaps the next day, as the absence of any subsequent transmission becomes undeniable, the realization will settle in that what they received was not simply the latest in a continuous series, but the final one. The end of a conversation that began on the 5th of September, 1977, and continued without interruption for nearly half a century. What will that moment mean? I want to resist the temptation to make it mean too much in the wrong direction, to turn it into a tragedy, a loss, a defeat for human ambition. Because it is none of those things. Voyager was never supposed to last this long. The mission has exceeded every reasonable expectation, by margins so large they have stopped being surprising and started being simply extraordinary. The science it has returned has reshaped our understanding of the outer solar system, the heliosphere, and the nature of interstellar space in ways that will influence astronomy and planetary science for generations. The photographs it sent back of Jupiter's volcanic moons, of Saturn's impossibly delicate rings, of Neptune's wild blue atmosphere, of the pale blue dot, have entered the permanent visual vocabulary of our civilization. These things are not diminished by the ending. They are not retroactively made less by the silence that follows. The mission was worth doing. It was worth every dollar and every hour and every career invested in it. And the last signal, when it comes, will be the final proof of that worth. But I also want to resist the temptation to make it mean too little, to treat it as just another mission closing, another spacecraft reaching the end of its operational life, another entry in the long catalogue of things that human beings have built and then watched wear out. Because Voyager is not just another spacecraft. It is the only human-made object in interstellar space. It is the only physical artifact of our civilization that has crossed the boundary of the solar system and entered the galaxy beyond. Its last signal will be the last direct communication from that territory, the last data point from a place that no other instrument can reach, transmitted by a machine that cannot be replaced or repaired or extended. When it ends, a chapter in human exploration will close that has no immediate sequel. There is no Voyager 3 waiting to take its place. There is no mission currently approved and funded that will put another spacecraft in interstellar space within any timeline that feels human-scaled. The last signal will not just be Voyager's last word, it will be, for the foreseeable future, humanity's last word from beyond the heliosphere. There is a concept in Japanese aesthetics called mono no aware, sometimes translated as the pathos of things, or the bittersweet awareness of impermanence. It is the feeling you get when you watch cherry blossoms fall, knowing that their beauty is inseparable from their brevity. It is the emotional register of things that are beautiful precisely because they will not last. I don't know whether the Japanese philosophers who developed this concept ever imagined it being applied to a spacecraft transmitter failing at the edge of the solar system, but I cannot think of a better frame for what the last signal will mean. Voyager has been beautiful, its journey has been extraordinary, its longevity has been improbable, and its science has been irreplaceable. And its beauty, the particular beauty of a small, determined, human-made thing, holding its connection across impossible distances for longer than anyone had a right to expect, has always been inseparable from its finitude. It was always going to end. The ending was always part of the story, and perhaps the ending is what makes the whole story worth telling. After the last signal arrives and is confirmed and processed and archived, Voyager will continue to exist. It will continue to move through interstellar space at 17 kilometers per second, following its long trajectory toward the outer galaxy, carrying its golden record and its silent instruments through a darkness that has been undisturbed for longer than our sun has burned. It will pass stars we have not yet named and regions of space we have not yet mapped. It will drift through the slow, cold history of the galaxy with the patience of an object that has no awareness of time. And in a sense, the sense that matters most, I think, it will still be speaking. Not in radio waves that our antennas can detect, but in the simple fact of its continued existence, in the act of moving forward, in the persistence of the human impulse that sent it outward in the first place, the impulse to reach beyond what is comfortable, beyond what is known, beyond what is survivable, toward whatever might be out there in the dark. That impulse does not end when the signal does. It is older than Voyager, and it will outlast the silence. And on the quietest nights, when you lie still and let the darkness be what it is, you can almost feel it. That ancient, unkillable human reaching, still going, still moving outward, still listening for something it cannot yet hear. We have travelled a long way tonight, you and I, from the antenna dishes listening in the California desert, to the volcanic surface of Io, to the impossible rings of Saturn, to the pale blue dot suspended in a sunbeam, to the heliopause where the sun finally lets go, to the hum of interstellar plasma recorded by an instrument, no larger than a briefcase crossing a void no human will ever cross in person. We have sat with the mathematics of final silence and the bittersweet arithmetic of fading power. We have thought about the people who spent their lives listening and the golden record drifting forever through the dark, and what it means to send a message into silence knowing silence is the most likely reply. And now, in the last quiet minutes of this journey, I want to offer you something that is not science and not history, but something closer to what all the science and history has been quietly pointing toward the whole time. Voyager 1 is a mirror. Not a literal one, it carries no mirrors, and there is nothing nearby to reflect in any case. Nothing but the thin, cold medium of interstellar space and the distant, indistinguishable stars. But it is a mirror in the deeper sense, the sense in which any human creation, carried far enough from its origins, reflects back to us something essential about the nature of the beings who made it. What does Voyager reflect? It reflects our longing, the ancient, unkillable human longing to know what is out there. Beyond the next hill, beyond the horizon, beyond the ocean, beyond the atmosphere, beyond the solar system, beyond the heliosphere, beyond the edge of everything we have ever been able to measure or touch or even adequately imagine. This longing is not rational. It does not serve an obvious survival purpose. It costs enormous resources and produces no direct material return. And it has been driving us outward, relentlessly and irresistibly, for as long as we have been the kind of creature capable of wondering what lies beyond the place we already are. But Voyager reflects something else too. something that I think is even more remarkable than the longing, because the longing is easy to romanticize. Voyager reflects our willingness to care about things we will never personally experience. The people who built it knew they would never travel to Jupiter, never see Saturn's rings from the distance at which Voyager photographed them, never stand at the heliopause and watch the solar wind fail. They built it anyway, built it with extraordinary care and ingenuity and dedication, so that the instruments could go where they could not and report back what they found. They gave the mission their best years and their deepest expertise, not for personal gain or personal glory, but for the expansion of a shared understanding that would outlast them. The science Voyager has returned will be studied and built upon by researchers who were not yet born when the spacecraft launched. The photographs it took hang in the minds of millions of people who have never met a single member of the mission team. The golden record drifts through interstellar space, carrying the voices of people who are now dead, toward an audience that may not exist, in a gesture of connection that transcends every boundary of time and space and personal mortality. This is what human beings do when they are at their best. They build things that are larger than themselves and send them forward into a future they will not live to see. I want to say something about the silence that is coming, because I think it deserves to be understood not just as a loss, but as a completion. Every great thing has a shape, and part of that shape is its ending. The fact that Voyager's signal will one day stop does not diminish the journey. It completes it. It gives the story the form that all stories require: a beginning, a middle, and an end that means something. The beginning was a launch from a Florida launch pad on an autumn morning in 1977, a small golden machine climbing away from the only world it would ever know. The middle was nearly 50 years of motion and discovery and connection, across distances that should have made connection impossible. And the end will be a fading, quiet, gradual, dignified, as the power that has sustained the voice across interstellar space finally drops below the threshold of transmission, and the signal that has been crossing the void for half a century completes its last journey and arrives at our antennas for the final time. That ending is not a tragedy, it is a punctuation mark. And the sentence it concludes is one of the most beautiful sentences our civilization has ever written. Here is the thing I keep returning to. In the deepest part of this thought, the universe is approximately 13.8 billion years old. For almost all of that time, for the first 9 billion years or so, there was no one in it capable of wondering about it. Stars formed and burned and died. Galaxies collided and merged and separated. Black holes consumed matter and radiated energy into the void. Supernovae seeded the interstellar medium with the heavy elements that would eventually form rocky planets. All of this happened, in the technical sense, without being observed, without being wondered about, without being found beautiful or terrifying or strange. And then, on one small rocky planet orbiting one ordinary star, something happened that had never happened before in the history of the universe, as far as we know. Matter became aware of itself. Atoms arranged themselves into structures capable of looking outward and asking, what is all of this? Where did it come from? How large is it? Are we alone in it? We are, as Carl Sagan said in words that have not lost their power through repetition, the universe noticing itself. We are the cosmos looking at its own reflection and finding it, against all expectation, astonishing. Voyager is the most literal expression of that noticing that our civilization has yet produced. It is matter. Ordinary atoms of aluminum and titanium and plutonium, forged in the cores of ancient stars, assembled by human hands on a planet that itself formed from stellar debris. It is that matter, reaching back out toward the stars it came from, carrying instruments designed to measure and record and transmit, maintaining a 47-year conversation with the beings who built it about the nature of the space it is crossing. It is the universe, in a very real sense, examining itself, sending a small piece of itself outward to report back on what the edge looks like, what the heliopause sounds like, what the magnetic field of the galaxy feels like to an instrument sensitive enough to detect it. And when the signal finally stops, when the last transmission completes its journey, and the frequency goes quiet, it will not mean that the noticing has ended. It will mean that this particular act of noticing has reached its natural conclusion, and other acts will follow, other missions, other instruments, other moments of contact between the universe and its own self-awareness. The silence of Voyager will not be the end of human curiosity. It will be an invitation to the next question. Thank you for spending this time with me tonight. Thank you for staying with the story of a small golden machine and the long, faithful signal it has been sending home across the dark. If something in tonight's journey moved you, if you felt even briefly that vertigo of scale and that strange warmth of wondering, then take a second to like this, or to subscribe, so that more curious minds like yours can find their way here. It means more than you might think. And now, let the darkness around you be comfortable. Let the silence be the good kind of silence, the kind that holds rather than empties. Somewhere out there, right now, a spacecraft is moving through interstellar space at 17 kilometers every second, carrying human voices and human music and a child's hello towards stars we have not yet named. It is still going. It will keep going long after both of us are gone. And the next time you step outside on a clear night and look up at the stars, really look past the familiar ones, past the edges of what you can name and the boundaries of what you can imagine. Remember that we sent something out there. Remember that it is still moving. Remember that we are the kind of creature that does things like that. And sleep well tonight, knowing that the universe is very large and very old and full of things worth wondering about. Good night.